Welcome back to ECE 501B. I didn't place as an announcement that you maybe need to be watching the D2L. I might actually make an extra video since we're missing Monday's lecture because of a holiday. I don't want to shortchange you on content or material. So watch, and maybe I'll send out an email if such a thing happens. I'm not sure when that will take place, if it will. But there are two things, and I need to make homework 2 available maybe tomorrow. Homework 1 is due Monday. Homework 2 is due a week thereafter. And homework 3 will be due prior to exam 1. And exam 1 is on the 30th. And I'm thinking homework 3 might be due on the 28th on a Monday evening also. That's what I'm thinking right now. We have barely begun chapter 2. And chapter 2 will be the material for homework 2. Chapter 1 was homework 1. And we will get into chapter 3 prior to exam 1. That's what I'm planning to do. Chapter 2 is finite dimensional vector spaces. We are now trying to discuss today these concepts of span, linear independence, and if we have a vector space that is completely spanned by vectors, and those vectors are linearly independent, then that will form a basis, a set of basis vectors, and we'll talk about that too. But the plural of one set of basis is what I've indicated here as the plural basis. We could have many different bases for the same vector space. Then we will try to, once we've talked about linear independence, the obvious connection is linear dependence of vectors or elements in the vector space, and there's a linear dependence lemma, and those concepts then naturally lead, once we start restricting to a finite number of basis vectors, that leads us into this concept of dimension, and we're trying to now restrict our attention, as we said last time, in right now the left side of this diagram. We're trying to stay in finite dimensional vector spaces. That gives us this linear algebra material in the first textbook. When we extend these concepts to infinite dimensional spaces, then we will be into functional analysis, which is the Frank's text, just as a reminder of where we are located on the map, on the global map of finite and infinite. Here is finite, just quickly as a review of what we talked about last time. We defined the span of a collection of vectors to be wherever we can get to with a linear combination, where that linear combination is using scalars from our field of numbers, f, and that field could be either the reals or complex. That's what the f means. And we started with an example, and we actually finished that example in one way. I want to maybe look at that a little bit differently today, and then we'll pick up after that example. Suppose we're given two vectors, 3, 3, and 4, 5, and since these are in R2, that's our vector space, we can actually think of these as an x-coordinate and a y-coordinate. We want to know what's the span of those two vectors, and if we sketch those in a graph, I tried to be a little bit more accurate in this graph, and it emphasizes the fact that those two vectors are not too far apart in terms of their orientation. There's a small angle between those vectors. We'll learn a little bit about angles later on in the course, but you can see that those two vectors are not quite on top of each other. And the fact that they are not quite on top of each other allows us now to actually get to any point we want to in the vector space, which is R2. Last time we did the solution, started by the definition, saying it's a linear combination, and we're restricting now our scalars to be in the field of real numbers. And if we scale 3, 3, and 4, 5 with these two scalars, A1 and A2, and position those quantities in the appropriate components of the last line's vector, then the first component becomes a linear combination of 3 and 4, and the second becomes a linear combination of 3 and 5. And we labeled those components Z1 and Z2. If we set that up in a matrix representation, then we have Z is equal to, let's say, M, a matrix, times a vector A. If we simply invert that matrix M, we found that we have then A's, A1 and A2, written in terms of the Z's, Z1 and Z2, and if we can now find values for A1 and A2 for any particular choice of Z1 and Z2, then that spans all of R2. And we can see that that's true for this particular collection of two vectors, 3, 3, and 4, 5. If you are matrix inverse averse, if you don't care to do things in terms of matrices and their inverse, you could say, well, can I just have two equations in these two unknowns, compare these equations, and yes, you have a Z1 equation, you have a Z2 equation. The nice thing here is that there's a 3 in common with both of those as far as the coefficient for A1 is the same in both of those equations, which now allows us, if we subtract those two equations from each other, it immediately eliminates one of those coefficients, A1, and now we can solve for A2 by negating that left-hand set of relationships to obtain A sub 2 is Z2 minus Z1, and in fact that's what we had in the matrix solution. It should give us the same answer. If we then use that information for A sub 2 in one of those two equations, let's say we use it in the Z1 equation or in the first equation, we have 3A1 plus 4 times what A sub 2 is, which is just the difference between Z2 and Z1. Do the algebra, and indeed we end up with exactly the same relationship relating A1 and A2 to Z1 and Z2 that we had doing a matrix inverse. If you like to think in one way or another, or this just demonstrates that there's many paths to the same destination. Which really we can conclude then that for any choice of these two coordinates, Z1 and Z2 in R2, so Z1 and Z2 are living in the set of real numbers, then the span of V1 and V2, those 3, 3, and 4, 5 vectors, will span all of our original vector space, which was R2. If we pick a specific point, Z1 being 1 and Z2 being 0, then we can find the values for A1 and A2 using the relationships that we've just derived to find that we need 5/3 of V1 and minus 1 of V2 to achieve that location 1, 0 in R2. And that's what we were wanting to show for any generic point Z. And here was just one specific illustration or location in R2. Basically, the unit x direction vector and nothing in the y now is some linear combination of V1 and V2, and the specific combination is A1 times V1 and A2 times V2, where A1 is particular 5/3, and A sub 2 is minus 1. That's what we can do when we talk about span. We can also think of span in terms of the following proposition, where now the span of any list of vectors in our underlying vector space V actually forms a subspace of V, is a subspace of V. Now if you give me any vector in your vector space V, and you want to know what's the span of any collection of those vectors, that collection will actually indeed form a subspace. Yes? So now the question is, can the vectors that you're picking in this list to form this list, can they be collinear? That was the question. Or can they be lined up in the generic sense of lined up? And the answer is yes. We haven't yet talked about any of this linear independence or linear dependence. All I'm saying here is a list of vectors, their span will form a subspace. And there could be redundancy in those vectors formed in or creating this list. But what do we need to do, or how can we show that in fact this proposition is a true statement? You probably just believe it, but what is needed if somebody said, I need you to prove that this list of vectors from the vector space V, the span of that list is indeed forming a subspace? What is needed to show a subset of V is a subspace? So if you give me some vectors from a subspace or from a vector space, I can say, well, you've given me a subset from that vector space. Now what this proposition is saying is no matter what you give me in terms of vectors from that vector space, they will create a subspace. And what did we agree to or conclude earlier about verifying that something is a subspace? So let's just say that suppose we start with a collection or a list, and that list now forms U, which is a subset. Does U have to have in terms of properties in order for us to conclude that U, in fact, is a subspace? Okay, so it has to have, I'll repeat them in the order that they were stated. It is closed under addition. It has to be closed under scalar multiplication, and it has to have a zero element or an additive identity. It needs three properties, doesn't it? It has three properties that we need to uncover. One of those, and the typical way that I've listed these, is it has a zero element, or this is now our additive identity. It needs to be closed under addition, which just means if you pull two vectors out of that subset and add them together, then the sum of those two vectors better be in the subset. And finally, it needs to be closed under scalar multiplication. let's see if we can justify that any collection of vectors from a vector space forms a subspace. Let's say that we are given a list of vectors, and I'm going to collect all of those into a list that I'm going to call W. W is now this list of V1, V2 up to V sub n. Oh no, sorry, Nevada, but Michigan. So we'll terminate at Michigan, M. I say that because you may not be able to hear my enunciation of M and N. I may not enunciate well, so that's why I use these states to refer to Nevada, N, or M as Michigan. This is now V1 through V sub M, or Michigan. Suppose we've pulled that out. That's our list of vectors in the vector space V. The span of W, what's another way of phrasing that? In terms of some of the variables that I've identified here. So I'm sure you heard that through the microphone. Maybe not, but the wording was scalar multiplications of the vectors all added together. And I'm going to condense that and say all linear combinations. The linear is now the sum and scalar multiplication combined. All linear combinations of vectors V sub I that we've placed in this list W. Now, we picked all of those vectors from V, so all of those elements of the list, or all of those vectors, inside the argument of the span, so now we're saying the span of those vectors are elements or vectors of our vector space V. And since V is closed, the original vector space, in order for it to be a vector space, it needs to be closed under addition and scalar multiplication, which are the operations used in forming linear combinations, are what we have. So now all of those vectors or elements in the span are vectors of V, and since V is closed under addition and scalar multiplication, then we can conclude that the span of W is in fact a subset of V. The span of W is a non-empty set. Now, what we want to do is show that it obeys those properties. Suppose I said, here's the zero vector. How can I build the zero vector from the list of vectors in W? Well, I can scale V1, I can scale V sub 2, and I can continue scaling in the same way all m of those vectors. And since a linear combination of the vectors are in the vector space V, then I have the left-hand side, which was what I started with, the 0 vector, is in fact in the vector space V. Or the 0 element is an element of the span of W, which says then that the additive identity exists. So that's property I, or the first property. We do have the additive identity in, or the 0 vector, or the 0 element in our subset U. Next, we want to take, let's say, W1 and W sub 2 that belong to the span of W. If that's the case, how would we, or what's one way of writing W sub 1? Just as some linear combination of the V's. And I'm going to subscript those with a double subscript because I have two different W's, a W1 and a W sub 2. W1, I'm going to say A sub 1, and the second subscript 1 is because it's scaling V1 plus A sub 1, 2, scales V2, etc. A sub 1 M scales V sub n. If W1 is indeed in the span of W, then I can find W1, or an expression for W1, as a linear combination of those V's. Likewise, I can rewrite, or I can express W sub 2 as A sub 2, 1, V1, A sub 2, 2, V2, plus A sub 2, M, V sub n. Yes? These V1 through Vm are just what I pulled from the vector space capital V and formed this list of vectors that I'm calling W. There's no number or numerical value for M relative to maybe the number of coordinates in these vectors V. I haven't specified that at all. I'm just saying that I have Michigan vectors in this list that I'm collectively calling W. And now in this part that I'm working on now, I simply said, let's identify two different vectors that are contained in the span of W. And by definition, if they're in the span of W, I can somehow find scalars to use to linearly combine those M vectors to create or produce W1 and W sub 2. Now I can add those two vectors together. And now again, since these A's are coming from, or those are scalars in my field F, and those sums are again scalars in F, and now I just have different scalars that are scaling the V1 through Vm. Let me try to phrase that. Let me say then that all of these coefficients are elements in F where F could be either the reals or the complex field of numbers. F is a field of numbers, and by definition of a field of numbers, that's closed. So which is closed under addition. Which then means that whatever I wanted to call this could be a alpha 1, and this could be an alpha 2, etc. And all of those alphas are now in this field of numbers, which allows me then to say that the span of W, whoops, getting ahead of myself, therefore the span of the sum or their sum, W1 plus W2, is in the span of W. And since those W1s and W2 were arbitrary, I can now say that the span of W is closed under addition. So now I've done property 1, 0 element. I've done property 2, which is closed under addition. And the very first thing was I looked and found that it was a non-empty set. So now the fourth one is going to show the third property, which is let's take W1 to be contained in the span of W. And let's let B be some scalar from our field of numbers. Again, we can represent W1 as A1V1, A2V2 for some coefficients. And now if we scale W1 by this scalar B, then we have B A1 V1 plus B A2 V2 again, we can see that since this field of numbers is closed under scalar multiplication, then the B A sub i's or B A sub j's are in the field of numbers, and so this is now closed under scalar multiplication. So we could say, but the B A sub j's are likewise elements of this field F, since F is a field and it is closed F is closed under scalar multiplication. Thus, this vector is a linear combination of the V sub i's. And that says then that the span of W is closed under scalar multiplication, and that then says that the span of W satisfies all three properties, and the span of W is a subspace of V, where W was just this list of vectors, and we hadn't said anything about the length or the number of vectors in that list. Just calling it a list, though, tells us it's a finite number of vectors in that set. We can make some comments or notes about what we've just through. One is the span of a list of vectors is actually the smallest subspace that contains these vectors. You give me a list of vectors, and now you take the span of that list. That's the smallest subspace that you can have that contains that set of vectors. And we can also talk about a relationship. There is a relationship to the concept of subspace sums. If W is a list of all vectors in subspaces, let's say U1 and U sub 2, can we define the span of W in terms of those subspaces? So if W is a list of all vectors in subspaces U1 and U2, then what can we say about the span of W? Pardon? So it's not the union, but the sum of U1 and U2. We want to distinguish between union and sum, because if we said the union, then you could just have the x-axis and the y-axis. We want the sum. The thought process is there. We do want to combine U1 and U2, but we want to do that as a sum and not as a union of those subspaces. But if you think about this, that list of W, if it has all of the vectors in the subspaces U1 and U2, how big is that list? It's huge, isn't it? If it contains all of the vectors, this could be very large, and we don't need all of that. So now we're getting to this question of redundancy, or can we kind of pare down what we're having in order to maybe span U1 and U2. We don't have to have all of the vectors. However, we will soon, let me say soon, see that this spanning set that we were calling W, we were spanning W, is able to be reduced in terms of the number of vectors. And to help us with that, let's just establish some terminology. Again, we're still looking at notes. The first note was the span of a list of vectors is the smallest subspace that contains these vectors. If we had a list of vectors and they were coming from, or they were the list of all vectors in subspaces U1 and U2, then we've got this mix of all these vectors and some vectors. Let's establish some terminology so that we can maybe more clearly articulate some of these concepts. Suppose that we now say if the span of V1, V2, up to Nevada V sub n is all of the vector space V, then the vectors V1, V2, V sub n are said to span V. If we take a list of vectors and the span of that list of vectors covers the entire vector space, then we will use a shorthand and just say that set of vectors span V. That means it covers all of V, or we can get anywhere we want in the vector space by linear combination of those vectors. Now, we haven't really gotten that far into Chapter 2 because we said Chapter 2 was finite dimensional vector spaces. We're just now introducing this notion of being finite. A vector space V is said to be finite dimensional if it is possible to construct a finite length list of elements, or you might even just say vectors, that span V. So if that Nevada list doesn't have to be infinite, if it can be finite, then, and it still spans all of our vector space V, then we say that that vector space is finite dimensional. And now that we have this notion of finite dimensional, we can start talking about independence and dependence of these vectors. Let's now look at linear independence. The vectors in a list, and let's say that list is V1, V2, up to V sub n, or V Nevada. The list, or the vectors in a list, are said to be linearly independent if the only combination of the vectors that equals the zero vector is the combination, or is the one, let's say combination, where all of the coefficients are 0. If you have a list of vectors and you claim that those vectors are linearly independent, then the only way that you can linearly combine those vectors to form the 0 vector is to use scalars that are all 0. You can write that in an equation form. You can say that is a1 v1 plus a sub 2 v2 plus a sub n v sub n is equal to 0 if and only if a1 is equal to a sub 2 is equal to dot 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 a sub n is equal to 0. That's an equation way of stating that those vectors v1 through v sub n are in fact linearly independent. Is the only way that they can combine linearly to give you the 0 vector is if those scalar multipliers are in fact 0. You could say that another way. This is equivalent to saying none of the vectors in the list can be written as a linear combination of the remaining vectors. Which if you had some non-zero coefficients there, then you would have that V1 is maybe some linear combination of V2, V7, V9, for example. You could just move some to the other side and find a relationship for an expression for V1 in terms of some of the other vectors. We can actually write a corollary to that statement, and that is that if a list of vectors is linearly independent, then none of these vectors can be written in terms of the other vectors. Let's see if we can argue our way through that corollary. And the way that I'm going to argue that is to use a proof by contrapositive. And what's the proof by contrapositive mean? If this corollary is A then B, or A implies B, then the contrapositive says we need to show that not B implies not A. And here, B is none of these vectors can be written in terms of the other vectors. So not B says we can write one of these vectors in terms of the others. And in this case, A says that the list of vectors is linearly independent. Not A says that the list is linearly dependent. This proof by contrapositive then says that we need to show not B implies not A. Now, to make this happen, let's just establish the subscripting notation. Let's just say that suppose the list of vectors that in the theorem is supposed to be linearly independent. Suppose the list of the list, oh boy. Suppose the list of vectors are labeled such that we have this not B condition. Where the not B is going to be written as V sub n is some linear combination of the earlier n minus 1 V's. Since we want to show not B, which is that one of these vectors can be written in terms of the others, let's say that V sub n, we've labeled these vectors such that we can say V sub n is A1 V1, A sub 2 V2, A sub n minus 1, V sub n minus 1. With at least one of these coefficients on the right-hand side not equaling 0. So all of these vectors, V1 through V sub n, are non-zero vectors. And we want one of those coefficients to at least be non-zero, so that we can express one of the vectors, which we've labeled V sub n, as a linear combination of the others. If that's the case, what if I go ahead and subtract, or basically add 0? And 0 here is going to be, what if I take V sub n from itself? I can even do that math. That gives us 0. That's the 0 vector, but in that sense, if we do that subtraction on the right, we have A1 V1 plus A sub 2 V2 plus A sub n minus 1 V sub n minus 1 minus V sub n. But what does that tell us? That says then that A1 V1 plus A sub 2 V sub 2 plus A sub n minus 1 V sub n minus 1 minus V sub n, that's equal to the 0 vector. But we also know that in an earlier step, we required one of those A's to not be equal to 0. And we know that that minus 1 that's scaling V sub n is also a non-zero scalar. So we have plus minus 1 V sub n. That equation there is equal to 0 with at least 2 coefficients, the minus 1 and one of the A's, being non-zero. And that particular statement is actually the not A, right? We wanted a list of vectors to be linearly independent, which says that the only way that that combination can be the zero vector is for all of those coefficients to be zero. So now we see that the list of vectors in blue right there, list of vectors is linearly dependent. Which is a contradiction, which is what we were wanting. Now, what we want to do is look at the following, or maybe just answer this question. Can a list containing the additive identity be linearly independent? Is it possible for a list that contains the additive identity, can that be linearly independent? And if you have an answer, now I give you the option. You could say yes or no, why or why not. So now if I give you a list, and that list contains as one of its vectors the zero vector, is that list linearly independent? What's the answer? No. And the justification for that? We could say, okay, if it's going to be linearly independent, we need to combine all of these. Let's say that now I have this. But I need all of those coefficients to be zero in order for that right-hand side to be zero. And if I have the zero vector in my list, what can you tell me about that guy? It's arbitrary, isn't it? That can be anything we want. And we can't have that. It has to be zero for that list of vectors to be linearly independent. This coefficient can take on any value, or can be arbitrary, can take any value. Without affecting the sum. The conclusion then, you can't have the zero vector in your list of linearly independent vectors. Now, we've talked about linearly independent. Let's talk about linear dependent by looking at the following lemma. The linear dependence lemma, which is in the second edition of Axler on page 25. Here it says, given a linearly dependent list, A it is possible to find an element or a vector of the list that is expressible as a linear combination of the remaining elements in that list. Or that is, or i.e., it's in the span, one of those vectors or an element, it's in the span of the other elements. So that's the first part, or the first half of this linear dependence lemma. If you have a linearly dependent list, then it's possible to express one of those vectors in the list as a linear combination of the others. Yes. Yes, if the vectors are, if you have a linearly dependent list, then you have to have one of the vectors capable of being written as a linear combination of the others. Proof is similar to what we just did above. I mean, we just write them out and we find by the labeling of those vectors, we can now write one in terms of the others. Let's just look at an example so that we're all on the same page. We won't prove it, but let's look at an example. I mean, we won't give a proof of part A, but let's just look at an example of part A. Suppose we have W1, and it's a 3 vector. That's 1 minus 2, 1. W sub 2 is minus 2, 1, 1. Whoops. Minus 2, 1, minus 1. And W sub 3, let's say, is minus 4, minus 1, minus 1. And we are interested in W, which is now this list of vectors, W1, W sub 2, and W sub 3. Now you can see that I've overloaded some of this notation. These are vectors, not components in a vector W. W is this set of 3 vectors, W1, W2, and W3. Do you see how to combine any of those to create the other? Let me give you a hint. Let me say that W3 can be written as a linear combination of W1 and W2. So let's say that we have W3. I'm going to run out of space, but here's W3, which is -4, -1, -1. And I'm saying that's some linear combination of W1 and W2. So now it's 2 and 3, isn't it? So if I pick a 2 on W1 and scale W2 with 3, we know the bottom has to be differing by basically a factor of 1. So we have 2 minus 3, that gives us -1. The second component then is -4 plus 3, that's -1, and the top component is, on the right-hand side, -6 plus 2, or -4. In fact, these do have a linear dependence characteristic. W3 is then in the span of W1 and W2. That's an example of part A of the linear dependence lemma. Part B is the following, which I haven't yet stated. It says removing a linearly dependent element from the list. Here I'm starting with a list that's linearly dependent. Now I'm going to remove a linearly dependent element. So in the earlier example, I would remove W3 from that list of 3 vectors. Removing a linearly dependent element from the list produces a new list with the same span as the original list. Which, if you just go back to the earlier example, what I'm saying is if you look at the span of W1, W2, W3, that's equivalent to the span of W1, W2. W3 is not giving you any new direction or any new information. Can we show that mathematically? So what's the proof of B? Let's now say that we're given, or we're beginning with, a linearly dependent list. So given a linearly dependent list of vectors, we'll call that list W, which is V1, V2 up to V sub n, or Nevada long, and a vector that is in the well, let me say this, and a vector that is in the span of this list What does that mean? So given a linearly dependent list of vectors W and a vector that is in the span of this list, U is an element of the span of the W, I can write that, or this means that I can now say U is equal to, let's say, alpha 1 V1 plus alpha 2 V2 plus alpha sub n V sub n, for some scalars alpha 1 through alpha sub n. Is that okay? So all I've done is I've just picked a vector that's contained in the span of that original set of vectors V. But we can also express, by the appropriate labeling of the vectors, but we can express V sub n in terms of the other vectors. Meaning we started with a list that was linearly dependent. V1 through V sub n is linearly dependent. So now let me just say that V sub n is one of the vectors in the list that's linearly dependent on the others. I'm going to label V sub n now as, let's say, minus A1 over A sub n. I wouldn't have to get this fancy, but I now saying that I had A1 through AN equaling 0. Now I have A2 over AN V2 minus A sub n minus 1, A sub n V sub n minus 1. Where I was actually using the fact that I had A1 V1, A2 V2, plus A sub n V sub n equaling 0, where my A sub n was one of the coefficients that I'd assumed was non-zero by the appropriate choice of vectors. Well, now if I have V sub n written in terms of V1 through V sub n minus 1, do you see that I could now replace that V sub n in my description for U? And now U is only a linear combination of the first n minus 1 V's. I really just started with an arbitrary vector in the span of V1 through V sub n. Now what I've done is I said, well, if V1 through V sub n is linearly dependent, then I can rewrite one of those vectors at least in terms of the others. And I just said, let me make that V sub n. Now I have V sub n in terms of V1 through V sub n minus 1. I'm going to use that fact to get rid of V sub n and write that in terms of V1 through V sub n minus 1. And now I have U in terms of n minus 1 V's and not n V's. So now I can write U as beta 1 V1 plus beta 2 V sub 2 plus beta sub n minus 1 V sub n minus 1. This is now a linear combination of n minus 1 vectors. And that allows us to actually conclude that U, the vector U that we arbitrarily started with, is actually contained in the span of a shorter list of vectors v1 through v sub n minus 1. Question? So now the question is, in curly brackets, a1 v1 plus a2 v2 plus a sub n v sub n equaling 0, why can I make that statement? Or one, there's two reasons I'm making that. One, I want to rewrite v sub n as a linear combination of the others, and I'm actually assuming that a sub n is non-zero. How can I do that for this equation? The only way that any of those coefficients can be non-zero is if this list of vectors is linearly dependent. And that was the first statement in our lemma. We are saying way back here that given a linearly dependent list of Nevada vectors, then we can make the following claim, that removing a linearly dependent vector, and in this proof, I'm assuming that linearly dependent vector is v sub n. I made that curly bracketed expression because those vectors are linearly dependent. Does that help? Okay, so let me see if I can continue this. So now we arbitrarily picked u to begin with in this proof, and I can then say, but u was a completely arbitrary element of the original span v1, v2, v sub n. Therefore, I hope you believe that the span of v1, v2, v sub n minus 1 is the same as the original span of v1 up to v sub n. Is that okay? Now, there was a comment that you had a second question, or did that answer it? So we haven't really gotten there yet. The question or the statement was, if I have a list of vectors that are linearly dependent, it's going to be very specific as to which ones are dependent, right? It's not arbitrary. In our list of W's, W1, W2, W3, here W3 was linearly dependent on W1 and W2. Now, we could have picked W1 and W3 and said W2 is linearly dependent on that. So it's some combination, but now that we know that we have this set or this list of linearly dependent columns, we can start throwing some away. And the ones that we want to throw away are the ones that we know are linearly dependent on the others. We don't want to be throwing away arbitrary vectors. So now, in this case, we were able to show, maybe, behind the scenes, that V sub n was a linear combination of the others. And now we are going to say that A sub n can be non-zero, and we can divide through by that. And now it makes our sort of discussion a little bit cleaner, because now we can just chop off the last vector in that list of vectors. And I think where I may pick up with this between now and the next time we meet, which is actually in a week, is with a couple more facts that use this linear dependence lemma and how we can throw things away. So I will see you in a week. Enjoy your long weekend. There is a homework assignment that you can enjoy over that weekend. And stay tuned.